Hi guys, welcome to the video for 5.2.2 where we're looking at circuits, resistance, and temperature. So let's jump right into this. Our first learning objective is to state that current passes through a resistor will inevitably heat it up. Now, if you recall Ohm's law from last lesson, you might think, Ohm's law says that for metals held at constant temperature, the current flowing through it will be proportional to the potential difference across it. So there's this idea that, if I pass current through a resistor, it's going to heat it up. But if it heats up, if the temperature changes, then it will also change other things as well. So what's going on here? So we have two types of resistors. We have ohmic resistors and non-ohmic resistors. Ohmic resistors are what I would call the typical resistors inside of a circuit. So those look like, they look something like this, okay, in terms of inside of a circuit. So they're tiny little guys about the size of an ant, and they generally do not produce any heat. So they follow Ohm's law and temperature stays constant. Non-ohmic resistors, you guys probably use this every day, is the light bulb. Okay, so a light bulb is meant to heat up. If you ever touch light bulb while it's on, you probably feel that it's quite hot and you might burn your hand. That's because they're meant to heat up to produce light. And so this is related back to like chapter 7, where it can emit, it's emitting radiation. Okay, so we want it to heat up and emit radiation, and so as a result of that, when it heats up, the resistance increases as well as it heats up. The more it heats up, the more the resistance increases. So one thing that you need to learn and recognize and maybe even sketch is the graphs for ohmic resistors and non-ohmic resistors. So ohmic resistors follow Ohm's law. So we have voltage and current, which means voltage over current is equal to resistance. And so this is your slope, right? So the slope of the line is the resistance, right? So it could be a 1-to-1 ratio, as you can see here. It could be 2-to-1, 1-to-2, 2-to-5 even, 2-to-5, 1-to-9, it doesn't really matter, okay? So the line could be of any slope, right? It could be straight up here, it could be over here, it could be over there, okay, it doesn't really matter. So that's ohmic resistors. This is now, we're looking at non-ohmic resistors. So as something like a filament lamp heats up, the resistance increases. And so the other thing that I want to mention is if you compare the two graphs, here we have a VI and then we have an IV graph. And so sometimes they like to do this to trick students in like a multiple choice section, paper 1. And they do this because most students have already memorized the graph is supposed to look like this. This is the more common one, okay? But be careful, be warned, look at the axes before you look at the curves, okay? The other thing is that this right here is what we call an LED light. So an LED light actually doesn't start at 0 voltage, it starts higher than that. And that's why they make good indicators for things like power switches. If your camera, like your webcam is on or not, you'll see that little green light, okay? So it's a good indicator for that because once the LED goes on, there's some voltage flowing through it. Okay, right now, this is an activity that we did in our class together. So I would encourage you to pause the video and then make a guess right now. Before you do that, just be warned, this is a resistance versus voltage graph. And, okay, so which of these guys is following the ohmic law, or sorry, the ohmic resistors or non-ohmic resistors? Make your guess either on a piece of paper or mentally. Okay, so hopefully you've had a chance to do that. And so resistance is meant to be constant in an ohmic resistor. So B and C both demonstrate that. And the ones where resistance is changing, these are the non-ohmic resistors. So D and A, where the resistance is changing. So with the resistance decreasing, maybe the light's being powered off, and A is where maybe the light is being powered on. Okay, there is an activity in figure 9, 5.2.2, and it's right here. Okay, so figure 9, 5.2.2. Check that out, follow those instructions, and go through that activity yourself, okay? It gives you a more pictorial diagram of some things that we've just talked about. Okay, lastly, we're going to apply Ohm's law. So V equals to IR, Ohm's law, to any part of a circuit. So some key reminders: current is constant in a series circuit, and the potential difference or voltage is constant in a parallel circuit. So here we have our series circuit. The total resistance or the equivalent resistance can be calculated by summing all of these guys together. Okay, so that's why this is 20. The current is constant. So if we had the current for 1 might be, say, 3 amps. Current for 2 would also be 3 amps. Current for 3 would also be 3 amps. The current for 4 would also be 3 amps. Okay? So all the currents are meant to be exactly the same. Now, voltage could be calculated. The individual voltage could be calculated, and then we can also add them all together to get the total voltage. So we know V equals to IR, so we just need to multiply everything. So V1 is 3 times 3, which is 9. And then V2 is multiplying these two guys together, 3 and 5, that's 15. V3 is 3 times 2, which is 6. And lastly, V4 is 3 times 10, which is 30 volts. And if we want the total resistance, sorry, the total voltage, that's going to be 60? Yeah, 60 volts. Okay? So just straight up add it all together. That's exactly what we just did. Okay, parallel circuit. So I think I just used similar values there. We'll just use the same 3, 5, 2, and 10. 3 ohms, 5 ohms, 2 ohms, 10 ohms. And if we want the equivalent resistance for this, we have to go through this set of calculations. Okay? And I'm going to go through this in a bit more detail because a lot of students do struggle with this. So the resistance total is 1 over 3, 1 over 5, 1 over 2, and 1 over 10. Okay, so let's see here. So I'm just going to punch that into a calculator. 1 over 10, 1 over 2, 1 over 5, plus 1 over 3. This is, we're looking at about 1.13 is the resistance total. So what we now need to do is to get the actual value, we need to inverse that one more time. 1 over 1.13. So 1 over 1.13. So we get 0.88. Okay, so I think I probably used some different values before, but this is now 0.88. Okay, and so voltage is constant in a parallel circuit, meaning if the voltage, I'm just going to do a little column over here. So if it was 3 volts here, it would be 3 volts here, 3 volts there, 3 volts there, okay? So that's going across each of these resistors right here. Now the current, we can add together. So to calculate the current, that's going to be I is V over R. So this is just going to be 1 amp, 3 over 5 is 0.6, 3 over 2 is 1.5. And 3 over 10 is 0.3 amps. Okay, and then so we can also calculate the total current by adding all of that together. So the total current is the sum of all that, so 0.3 plus 1.5 plus 0.6 plus 1 is 3.4 amps. Okay, so that's how you solve for parallel circuits. A little bit more complicated than series. Okay, in our example here, example number 3, a potential difference of 12 volts is applied across 5 resistors, 1, 2, 3, 4, 5 ohms arranged in series. So very important. The equivalent resistance, so that's just adding everything up together. That looks like it's going to be 15 ohms. So that's the equivalent resistance, or the total. The current passing through each resistor can be calculated from the V equals IR, so V total over resistance total, which would give us 12 volts over 15 volts. So 15 ohms. So 12 over 15 is 0.8. So the current is the same in the circuit. So you can always apply Ohm's law to the total of everything in the circuit, and you'll get the total current, which is the same throughout the circuit. I'm just going to write that a little bit more nicely, 0.8 amps, sorry. Okay, now the potential difference across each resistor. So V equals to IR, so we're just multiplying everything together. So I'm just going to do that right underneath here. So it's going to be 1 times 0.8 is going to be 0.8. 1.6. 3 times 8, 2.4. 32, so 3.2 amps and 4.0 amps. Okay, and if we're ever asked to, sorry, those are voltages, sorry, my bad. These are voltages. So these are voltages. Okay, and all of that should add up to 12 volts. So I'm just going to verify that. All of this should add up to 12 volts. So I'm going to verify my answer. 0.8, 1.6, 2.4, 3.2, 4. Yep, that's 12. Okay, so it allows you to verify your answer as well. Okay, question number 4. This time we're looking at a parallel circuit. So I think I forgot to write down the rest of this, but we want to figure out, so we've got resistance, potential difference, calculate the current, that's certainly C, CU, current passing through each resistor, and then you can also figure out the total current as well if you want. Find total current. Of the circuit. Okay, so to do the equivalent, there's, oh wow, didn't leave myself much room. So let me do this calculation. I'm going to do it above here actually. So I'm going to write the formula, 1 over R total. We have 5, R1, R2, R3, R4, R5. Make the substitutions. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. And so that is going to be, I'm just going to do this, 1 over 5, 1 over 4, 1 over 3, 1 over 2, plus 1 is 2.28. So remember that this is now, I'm just going to write this out separately. So now the formula is 1 over R total equals to 2.28. So that's not the actual resistance, so we have to flip that around, right? Resistance total is 1 over 2.28. So let's do that. 1 over 2.28 is going to give 0.43. Okay, and remember a little tip earlier is that the total resistance, or the equivalent resistance, should generally be smaller than the smallest value. And that looks correct, ohms. Okay, potential difference. So the voltage is the same, so it's always just 12 volts. 12 volts, right? The current will be different though, so current is V over, I'm going to do this here, so the current is going to be V over R. V equals to IR, yeah, V over R, right? So V over R. So 12 over 1 is 12 amps. Wow, that's a lot. 12 over 2 is 6 amps. 12 over 3 is 4 amps. Then 3 amps. And is that 2.4? 12 over 5, 2.4 amps. Okay, and then if we were to ask to find the total, we just have to add all that. So 12 plus 6 plus 4 plus 3 plus 2.4 is, that's 10, 22, 25, 27.4 amps is the total. Okay, I've got 2 more activities here, so feel free to pause this video in between to figure things out. These are things that I had just sort of made up for myself for your practice. So what's the resistance of R3? This is a series circuit, as you can see in the diagram. So 19 minus 10 minus 5, I'm just going to go quickly here. So pause the video, go through everything yourself. This is going to be 4 ohms. 3 amps is going through, so current is constant, so this is always 3 amps. So it's 3 amps here, 3 amps there, 3 amps there. This is the current. Potential difference across, so V equals to IR, so voltage is just multiplying everything. So 3 times 4 is 12, 15, and 30. And if we want, you could also add all those up for the total voltage as well. Okay, our next activity is another parallel circuit. So again, feel free to pause the video right now, find the solutions, okay? Again, the parallel circuit, because it's quite difficult, I'm going to go through it in full detail. 1 over 5, 1 over 10. Oh, sorry, we're asked to calculate this one this time. That's right. And so we're given that the resistance total is 1. So I'm going to make the direct substitution in there. So this is going to be, I'm going to do this as fractions, 10 over 10, that's the 1 over 1, minus 2 over 10, that's the 1 over 5, minus 1 over 10 is 1 over R3. So if we were to rewrite this, 1 over R, sorry, I'm going to just do this on the side. 7 over 10 is 1 over R3, which means R3 is flipping that around. So R3 is 10 over 7 ohms. Okay, so total resistance is just a little bit lower. It's going to be lower than our smallest resistance value. That looks right. Okay, so again, the potential difference of 5 volts across, so it's always 5 volts, 5 volts, 5 volts, 5 volts. Calculate the current. So current is V over R. So this is going to be, so the current here, so I'm sort of making a little table here on the side here. Current is going to be 1 amp, 0.5, and then 5 over 10 over 7. So that's 5 times 7 over 10 then, right? 3.5 amps. Is that right? 3.5 amps. Okay, let me just check that one more time. 10 over 7 is 1.4. 5 over 1.4 is 3.5 roughly. Okay, yep, that looks good. Okay, so that's a current, and then of course you can add all that up. That'd be 5 amps would be the total current. Okay, last little bit is I did this little example here with the class where if you were to sort of imagine that there's a group of people trying to get past, so the humans or the people or whatever are going to be the electrons, okay? And they're trying to get past these different people, and so they're going to experience some resistance because they're not going to let them through very easily. And so if you have a lot of people trying to get past, different people, including Mr. Leung, then most people are probably going to go to the path of Mr. Leung because the other people will destroy you. Okay, so you might get like one person going through. You might get one person going through Thanos. You might get like one person going through Thor. You might get one person going through Iron Man. Okay, and then you get like 30 or like 80 or 100 people going through Mr. Leung because, well, I don't provide much resistance. So that's roughly just to illustrate the idea of the parallel circuit, is that if people had the choice, electrons had the choice, they're going to take the path of least resistance, right? And so they're not going to want to go through something like Thanos. They're going to want to go through the easiest path, just like we humans do. Okay, guys, hope you get that, and let me know if you got any questions or comments. We'll see you guys in the next video. Take care. Bye-bye.